graphs. We talked about graphs last time. We talked about a position versus time graph. Class, remind me, what is the slope of a position versus time graph?
Velocity.
Velocity. Good. So now we're going to talk about a velocity versus time graph. Velocity versus time graph. So let's just say we have a line on there. Class, the symbol for slope is? M. The equation for slope is, class? Rise over run or? Delta y over delta. So we have rise over run, delta y over delta x, the change in the y position over the change in x position. We do not have a y-axis, we do not have an x-axis. Instead of having a y-axis, we have a velocity axis. So we have the change in velocity on the top. Instead of having an x-axis, we have a time axis. So on the bottom, we have a change in time. Which means, class, the slope, bless you, no, I'm not going to bless that, I apologize, I take it back. The slope of a velocity versus time graph, then, class, is?
Acceleration.
Acceleration. The slope of a position versus time graph? Slope of a velocity versus time graph?
Acceleration.
So you can see that these are related via the slope. We are, again, going to come forward and walk out graphs. Let's start with this velocity as a function of time graph. We are going to start, James, with you coming forward and walking this velocity versus time graph. You're not Carpenter, you're James. He's James. Right, you're Carpenter. James. James. James! Come forward. Now, James, remember to say start when you start, stop when you stop. Remember to, number one, not hurt yourself. But please, you can exaggerate for effect so that we can see what's going on. James!
Start. Stop.
James, go back. Go back over here. You need to exaggerate for effect so we can see what's going on. Did you? Are you good? Do you need to? I want you to try again. I'll exaggerate. James. James.
Start. Stop.
Okay, wait, we have a question in the back. I got it, Rachel.
Which side on the graph again is the left side and right side of the dot?
It's a fair question, and I can't answer that question at the moment, which is an interesting answer. We'll get to why I can't answer it in just a moment. Come on back. I'm white. Okay, interesting. We're all over the board. Okay. All right, Gershard, you were all in the James camp. Go ahead, tell me what he did. Tell me what he did right. Go ahead.
Kept a constant phase.
Constant phase?
No, phase. So like
Pace?
yeah.
I don't know pace. This is not a term I've used yet in this class. Right? We should use the terms, the physics terms. Pace does mean something, but we have yet to actually use it. Frank?
Constant increase in constant acceleration.
I had a hard time seeing that Frank had a constant acceleration. I had a hard time seeing it, Frank. He should, Brad.
You should get a constant velocity.
It really looked to me like it was a constant velocity. I do understand that this can be difficult sometimes, but you should be able to show an increase in velocity, Frank. Do you hear me?
Yeah.
James? Right? James. Okay, so we're going to try this again. James. Here we go.
Start. Stop.
Okay. I should have said that a little bit earlier. That's okay. Now come back. Now, so you see, he starts out slow and he accelerates all the way across. Thank you much. Okay, good. Now, let's get to, and I'm going to answer your question in just a moment. Let's get to where he should have started. Where does it say on this graph he should have started? Carpenter.
Middle of the
the middle of the desk. Yes? No. Does not say he should start in the middle of the desk. Maxim, what does it say about where he should start?
It doesn't specify.
Nothing. This is a velocity versus time graph. So your question is, what does this graph say about position? It doesn't say anything about where you actually should be. I'll review that in just a minute with the position versus time graph. But it doesn't actually indicate where you should start. Clearly, it makes most sense to start over here, not over there, because you don't want to run into the wall, right? So, but this doesn't actually indicate where you should start. So let's talk about the position versus time graph associated with this. So the position versus time graph, seconds and meters. So this was the middle of the desk, this was to the right of the desk, and this was to the left of the desk, just to review that piece for you. Now, it doesn't say where he's going to start, so I'm just going to start the graph right here. It doesn't actually tell us where to start, but we'll start it there for our purposes of our drawing here. Now, remind me, class, what is the slope of a position versus time graph?
Velocity.
Velocity. In other words, the slope of this graph is the velocity. So initially, class, what's the initial velocity? 0. So what should the initial slope be? 0. So initially, the slope should start out like this. As time goes by, class, what happens to the velocity?
Increases.
Increases. So what happens to the slope?
Increases.
Increases. So we should see the slope increasing as a function of time. So this graph is going to look like this, where the initial slope, using my magic tangent line finder, the slope starts like this at a slope of 0. As time goes by, I can draw tangent lines. I have a tangent line right here. You can see where the slope is slowly increasing as a function of time. That is the graph of position versus as a function of time that we should have for this velocity as a function of time. Right? Now, we're going to draw an acceleration as a function of time graph that goes along with this motion. The acceleration is a function of time graph. So let's review. Class, what's the slope of a position versus time graph?
Velocity.
We're going to try again. You're still slope. Okay. What's the slope of a position versus time graph?
Velocity.
What's the slope of a velocity versus time graph?
Acceleration.
So notice how I've set them up. The slope of this graph is this one. The slope of this graph is this one. For those of you who enjoy calculus, what's the derivative of position as a function of time? Not quite there yet. The derivative of position as a function of time is velocity. The derivative of velocity as a function of time is acceleration. Calculus. The integral of acceleration as a function of time is velocity. The integral of velocity as a function of time is position. Calculus. It's really, really helpful. Not a part of this class. Okay, so now we want to draw the acceleration as a function of time graph. Ash, thoughts?
I really have no idea.
Okay, so let's back up. Ash, what's the slope of a velocity versus time graph? No,
Acceleration.
the acceleration going this way. So the question then could be rephrased as, what do we know about the slope of this velocity versus time graph? It looks like that. Okay, so the question is, what do we know about this slope? Help us out. Alham.
It increases by a constant rate.
It does not. Okay, the velocity increases at a constant rate, but the slope has a constant value, right? The rise over run, the change in y or change in x, the value of this slope is the same because it's a straight line. Okay, so the slope is constant. So what does that mean for acceleration as a function of time?
It's constant.
It's constant. Well, how do I draw that?
It's just a straight line.
Now, here's the thing. When students say straight line, they mean something else, which they did not actually say. Because we already have a straight line for velocity, but that's not what you mean.
Line here parallel to the T.
We'll call it a horizontal line. It's easier to say. Okay? So realize, a lot of times when you say straight line, what you mean is a horizontal line, so you should say horizontal line. So I agree. Because this slope is constant, we should have a horizontal line on our acceleration as a function of time graph. True. We have an idea of where to draw it. We don't know specifically, but we do know something about the acceleration as a function of time, and we can draw it relative to the time axis. What do we know about the acceleration, the value of it? Frederick.
The acceleration is positive.
All we know is it's positive. We don't know its value, but we know it's positive, which means we need to draw a horizontal line above the time axis because our acceleration is constant and positive because the slope of the velocity as a function of time graph is constant and positive. So I got some blank looks when I said that the slope was constant. So I just want to talk about that for a brief moment. Okay? The slope of this line is constant. Remember, slope is change in y over change in x, the rise over run. So if you look at it, if you take any part of this, and I talk about the change in x and the change in y, and I know I have to draw pretty small to see that. Spencer, can you wait just a moment? George, you
Well, I don't know what graph that is. Is that acceleration?
that's velocity as a function of time.
All right.
okay.
Can you label them? 'Cause
I did. Velocity, position, acceleration. All of them is a function of time. So, I said the slope of this line is constant. At any point, if you take a value for the change in y and divide it by the change in x, you will get the same number. That's what it means that the slope is constant for the velocity as a function of time. Therefore, the slope is constant, therefore the acceleration is constant. We have a horizontal line. That's what that means. Let's do another one.